Hello everyone, my name is Kayla Croman. I'm a junior meteorology major here at WKU in the Department of Earth, Environmental, and Atmospheric Sciences. I'm excited that you can be here and listen to my presentation today on using streamflow forecasts in addition to soil moisture to indicate the impacts of floods in agricultural areas of Kisumu, Kenya. And I actually completed this project last summer, the summer of 2020, in accordance with the REU program, Research Experience for Undergraduates, and I partnered with NASA Severe here. NASA Severe is kind of a sister company of NASA where they use remote sensing and other satellite technologies to indicate where natural disasters are likely to happen in vulnerable parts of the world, both financially and just safety-wise. So with that being said, I wanted to focus on Kisumu, Kenya, for my area because Kisumu is actually responsible for 1/3 of the gross domestic product of Kenya in general because of their crop production. They produce things such as tea, maize, and sugarcane. So they really do carry the economy of the country in a way and overall food security with that being said. However, because of their location to Lake Victoria and other surrounding rivers, they are vulnerable to flash floods and even riverine floods. So with this being said, I went into further literature review and found that there's a gap between the time a flood forecast is released and the time that early actions are taken. So the purpose and goal of this project was to see if I could use not only streamflow forecasts, but also soil moisture to see if soil moisture played an impact in kind of predicting how severe these floods would be, because the impacts and effects of floods on how devastating they are does have to do with how wet the soil moisture is prior to that flood happening. So diving right in, I knew that I had to pick two floods of similar stream flow but had different soil moisture content. So starting out with stream flow, I used the historic stream flow prediction tool and found two floods in two different years, the first one in 2018 and the second one in 2019. And then I jumped down to finding soil moisture and was praying that I found different soil moisture values for those. And in fact, I did. And they actually only gave me 3 hourly geotiffs, but I needed daily geotiffs to represent each day, 2 weeks out leading up to the flood. And I averaged these values to find a mean in GIS. And then lastly, we, of course, wanted to create some visuals for the flood extent maps and wanted to estimate acres of crops impacted to see, what soil moisture values had the most effect on crops. And moving on into the analysis and results, the two charts up here, the top one represents the 2018 flood, and the bottom one represents the 2019 flood. The blue bars you see represent the stream flow, so we did accomplish similar stream flow forecasts for the most part. They both have an increasing trend overall, 2 weeks out from the flood and the day of the flood. And then the red line represents the SMAP value, or soil moisture, in other words, soil moisture wetness. So they are very different, which is what we were looking for. So the top 2018 flood, the top one here, you can see that it's pretty wet at coming in at values of 150, approaching 200 at times. And in 2019, it's actually much drier. So again, this is exactly what we wanted, two different soil moistures. And now we wanted to look at how the floods ended up. Where did the water go? What parts of Kisumu were impacted the most? And that's what these VV images down at the bottom of this analysis column shows, the before and after water spread of these floods, so to speak. And as you can see, sadly, we were disappointed to find out that these floods were not as widespread or impactful or devastating, as bad as that sounds, as we at first thought that they were. The 2019, you do have in the southern part of Kisumu here a difference in water before and after the flood, but for the most part, it's not significant enough to continue on with the research that we wanted to do. The data just wasn't supportive of it. We couldn't distinguish whether or not, the crops were impacted by these, only using this. There were even no field reports. We tried to find newspapers, but none were in existence as far as we know. Landsat, it was cloudy after the floods, so we couldn't see any apparent floods on any loops And again, this was just a researching fall. That's how research goes. Maybe the floods weren't as widespread or devastating as we initially thought. And we are also quite limited using SMAP. Those composites only go back to 2015. So just kind of our bold concluding statement here, soil moisture conditions, they are different leading up to floods of similar stream flow. However, we couldn't move on to distinguish flood extent over agricultural areas from Landsat. So moving forward in the future, if we had the time, we could look at full time series over every image over our study area for several years, even looking at backscatter anomalies in 2018 or 2019 in our crop areas. If we had access to something like L-band SAR or NISAR, we could possibly detect partially inundated crops. Looking at standing water, that would be very bright in those instances. But if we wanted to extend off of this particular research that we've already done, we could explore what the relevance of rainfall and/or soil moisture is in informing flood preparedness, and also can soil moisture composites serve to create better lead time and early action flood plans. So with that being said, I just wanted to thank the RIU program and other supporting services who made this project possible, and I look forward to hearing your questions very, very soon. Thanks.